Anybody can take the derivative of a function using basic calculus rules. But is it possible to take the derivative of a function without invoking boring derivative formulas? In other words, can we take a derivative without taking a derivative? That statement may seem self-contradictory, but it is satisfiable. Today, we're going to demonstrate this by taking the derivative of the arctangent function using geometry. However, before we demonstrate this alternative proof for the derivative of the arctangent of x, let's quickly review how this derivative is taken normally. This function is the inverse of another function, namely tangent of x. The derivative of an inverse function can be easily found by starting with the statement that for any function f of f inverse of x is always x, as a function undoes its inverse. Taking the derivative of both sides and applying the chain rule on the left side by first taking the derivative of the outside function f of x with respect to the inside function f inverse of x, and then multiplying this by the derivative of the inside function f inverse of x just with respect to x, we get the following equation. This can then be rearranged into the following form by dividing both sides by the first term in the product that came from using the chain rule. Now, this explicitly gives the derivative of an inverse function as the reciprocal of the derivative of the original function evaluated at f inverse of x. That's a little bit of a mouthful, but thankfully the statement that this equation is trying to make is actually quite simple and can be explained visually. Consider the graph of some function f, along with the graph of its inverse, f inverse of x. Now, notice that the graph of f inverse of x is simply the reflection of the graph of f of x over the line y equals x. This applies to the tangent lines to these graphs as well. For example, the tangent line to the graph of f of x here can be reflected about the line y equals x to find the tangent line to the graph of f inverse of x at its corresponding point. In the process of this flip, the slope of the tangent becomes inverted. This is what the equation from before was saying, that the derivative of an inverse function at any point x can be found by going to the corresponding point on f of x and then finding the derivative there, and then finally inverting the result. Now that we have a little bit more understanding of the underlying meaning of that equation, let's quickly rederive the derivative of the arctan normally. If we substitute in f of x equals tan x into the equation and use the fact that the derivative of tan x is secant squared of x, we get, after some simplifying, that the derivative of the arctangent function is 1 over 1 plus x squared. This is all well and good, but you're probably waiting for the interesting part where I take a derivative using geometry. Indeed, I will not force you to wait any longer. Let's begin trying to prove this derivative from a different angle. Unsurprisingly, if geometry is going to be the main tool I will hope to use to solve this problem, then I will be drawing a diagram to assist us. I'll begin by adding in some coordinate axes. Note that I've named the horizontal axis the t-axis instead of the x, as I will be using that variable later. Now, I'm going to add in this quarter circle that is part of the graph of the circle t squared plus y plus 1 whole squared equals 1. It is just part of a unit circle that is centered at 0, -1. At this point, consider a point on the t-axis that let's label x. It does not matter where on the t-axis that this point is located. It can even be on the negative side of the t-axis, as logic very similar to what we will be using shortly will still apply. However, we shall just keep it here as a general example. Notice that if we draw a line from the center of the circle at 0, -1 to the point x, 0, we form a right triangle with legs on the coordinate axes. The vertical leg of this triangle has a length of 1, and the horizontal leg has a length of x. As a result, if we label this angle to be equal to theta, then we're going to find using this triangle that theta is equal to the arctangent of x. Now, we can think of this angle as a function of x. Its size changes as we vary x in accordance with the arctangent function. Now that we have the arctangent function on our graph, let's try to take its derivative. To do this, let us recall what a derivative really means in regards to this problem. We want to find the derivative of theta, which is the arctangent of x. Its derivative can be written as d theta dx. Here, d theta represents a small change in theta, and dx represents a small change in x. To find the derivative of the arctan of x, we need to find the ratio of these two infinitesimal quantities. In order to do this, let's add these quantities to our diagram. Here's a small change in theta, d theta, that leads to a small change in x, dx. To find a relationship between these two infinitesimals, we will not be using calculus, but geometry. In particular, we will be using the technique of similar triangles to guide us through the rest of this process. You're probably wondering where the similar triangles that I'm alluding to are. In fact, they are currently not on the screen. We must construct them by adding in this line here. Once we do this, we form two similar triangles, a small one and a big one. Further, there is something interesting to notice here. The area of this small triangle is almost equal to the area of this small sector of this arc. The arc is just a little bit bigger than the triangle by this small area here. However, as we note that d theta was always meant to be an infinitesimal quantity, we see that as we let this difference in theta approach 0, the size of this small area that is the difference in areas between the triangle and the small sector approaches 0. I'll now go back to having the small change in theta being a little bit bigger as it was before to make it more visible, but it's important to understand that it can be said in reality, d theta is very, very small, and the area of the small triangle is exactly equal to the area of the sector in the limit that the change in theta approaches 0, which is the condition that we want to investigate as derivatives use such limits. You're probably thinking right now that this is an interesting statement, but how will it actually help us take the derivative of theta? Let me explain why this is useful. First, let's examine the area of this small white sector more carefully. The area of this sector is 1/2 r squared alpha, where r is the radius of the sector and alpha is its central angle. By the above equation, this area is equal to that of the small purple triangle. It is clear that this central angle is d theta, as this was how this sector was defined. Further, its radius is simply 1 as it was constructed on a translated unit circle. If we substitute these values for r and alpha into our expression, we get the following equation. This can then be simplified to show that the area of the small purple triangle is just half of d theta. Why is this helpful? Well, it's because now we have an equation that gives the area of the purple triangle in terms of d theta. If we can find the area of this triangle in one other way that involves dx, we can equate the resulting expression with the one we just found to solve for d theta dx. And luckily, the similar triangles from before give us just the way to do that. First of all, let's establish rigorously that these two triangles over here are similar. They are similar because they share this angle over here, and due to these two parallel segments, these other two pairs of angles are also the same. Thus, these two triangles share all the same angles, and thus they are similar. We can use this fact to help us find the area of the small triangle in a different way. Consider this long side of the big triangle. It is the hypotenuse of a right triangle with legs on the coordinate axes. One of the legs of this right triangle has a length of x. The other has a length of 1. Using the Pythagorean theorem, which states that the length of the hypotenuse of a right triangle is the square root of the squares of the lengths of the legs of the triangle, it can be shown that the length of this side of the big triangle is the square root of 1 plus x squared. Now, we know that the radius of the circle is 1, so it follows that the long side of this small triangle is also 1. These two side lengths that we have just labeled, one on the big triangle and one on the smaller triangle, are corresponding sides of similar triangles. They can be used to show that the smaller triangle is scaled down from the larger one by a factor of s, where s is equal to 1 over the square root of 1 plus x squared. This means that all important lengths of this small triangle are s times the corresponding length for the big triangle. For example, this side length here corresponds to the horizontal side length of the big triangle, which has a length of dx. As a result, the side length has a length of s times dx. This scaling also applies to the heights of these two triangles. The height of the big triangle was 1, so the height of the small triangle is s times 1, or just s. We can now notice that we have just labeled the base and height of this small triangle. This will allow us to find its area in a different way that involves dx. The area of this triangle is 1/2 base times height, which becomes 1/2 s dx times s, using the values we have just found. Combining the like s terms leads to the simplification of 1/2 s squared dx. If we insert the equation for s that we defined earlier into this expression, we get, after a quick simplification of the square of a square root, that the area of the triangle is dx over 2 times 1 plus x squared in parentheses. We're almost done now. If we equate the two equations for the area of the purple triangle, we find that 1/2 d theta is equal to dx over 2 times 1 plus x squared. Canceling the factor of 1/2 on both sides, we are left with the following. All that really must be done now is to divide by dx on both sides to get d theta dx is equal to 1 over 1 plus x squared. If you recall that all along theta was the arctangent of x, then it is clear that what this equation is really saying is that the derivative of the arctangent function is 1 over 1 plus x squared. With that, we have now taken the derivative of the arctangent function with just geometry. Mission accomplished. Thanks for watching this video. If you enjoyed it, please consider supporting the channel by subscribing. Otherwise, I'll see you all next time. Until then, goodbye.